So hello, welcome to day 2 of chapter 24? Chapter 24. The chapter numbers for Physics 2 still mess with me up. We've been talking about induction, and by induction I mean induced EMF and currents. Basically, that if we start messing with, I got my flux, that if we have a magnetic field, here symbolized by these green pointy bits. If we have a magnetic field and we put a loop of wire in it, if we start changing the flux through this wire of the magnetic field, we can induce a EMF, aka force a voltage on it, which means force a current through it. And we can do this by changing, we do it by changing the flux, which means either changing the magnetic field, being which way it's pointing or how strong it is, or by taking the loop and either changing the area of the loop or the area of the loop in the magnetic field or the angle of the loop. And we're actually going to pick right up with the talking about changing the angle of the loop. I mean, we ended last class with a bunch of examples about how we can induce a EMF with things like the guitars and the GFI and things like that by moving pieces around. But one of the more practical ways to induce an EMF is by messing with the angle. You see, flux is what causes what you have to do with a change EMF, right? Change in flux over change in time is how we find an induced EMF. But flux is BA cosine theta. When theta changes, that is one of the easiest ways to create an EMF. And this is what a generator is. A generator, or at least an AC generator, what it is it's something that converts mechanical energy to electrical energy. And this is commonly used. If you look at most types of ways that we as a society make power, like make electricity, be it more classic like coal and natural gas, something like that, or more modern like first I was going to say wasn't modern. I was going to say windmills. Windmills aren't modern, but modern windmills and hydroelectric. Almost all the ways we make electricity involves making something spin. Because here's the idea. If you can make something spin, you can make electricity using this AC generator. All an AC generator is I'm just going to use this for my magnetic field again, is if you start spinning the loop in a magnetic field, that when the loop's spinning, that means theta is changing. If theta is changing, we can go and say that that's a changing flux. And yeah, hydroelectric power is you have water push a turnstile, causing it to happen. Wind, you have wind turn a thing, causing it to happen. Coal power is you have coal producing steam, which turns a thing, causing electricity. Here's me playing around with one. And what you can see now that I have the side is when you look into this thing, you see these wires in here. You know what? Nah, I'll play. Those wires are just a series of loops of wires. Right now, not hooked up to anything that I can spin. And let me go back a tiny bit real fast. Well, I can do it from here. This whole piece around, this like flat looking U thing, you can see it from the side. These are magnets. That there's one big horseshoe magnet, actually 3 big horseshoe magnets on each side for a total of 6 magnets. Now I hook this thing up to a voltmeter, and I'm just going to start spinning that loop in the middle. And you can see as I spin the loop in the middle, I keep getting voltage. Now it's not very constant because I'm not spinning very constantly. And also it was staying positive because I had it set to AC. I'll come back to that in a second. But yeah, when this thing spins, I create electricity. That's the general idea. Now this does look a lot like a motor, right? A motor I showed that if we put electricity through something, we would make it spin. And it's actually true. A generator and a motor are basically the same thing. If you input voltage and the input of voltage causes it to spin, like a motor we talked about before, all that is it's just going in that direction. It's by inputting electricity, we cause a force on the wire causing the spin. That's a motor. But if instead you make it spin, and the process by making it spin, you cause electricity, that's a generator. But really, they're the same thing. It's just the order is different. And often you can use the same setup, and depending on what you do, either use it to put in electricity and create motion, or to use motion to create electricity. It's just where you apply the force. Now, here's the math involved. That if I'm spinning this loop of wire in a magnetic field, I'll say that the induced EMF is N times the change in flux over change in time. I'm doing an absolute value just to not deal with what direction the EMF is in. We'll come back to that. Also, there should be a negative sign in front, but once again, I'm not doing with direction right now. This means the EMF is N times the change in BA cosine theta over theta t. But if you have a generator, normally B isn't changing and A isn't changing. Now, to get from this step to the next step, some calculus happens. Don't worry about it. Really, these should be derivatives, not deltas. And so when this magical calculus happens, that's above the level of this class. So if you know your calculus, you probably know how this came from. You get this instead. From physics 1, though, we know change in angle, change in time is angular velocity. And so what happens is that an EMF is produced of NBA, the angular velocity, times the sine theta. But that means as it spins, the EMF changes. And a sine theta can go everywhere from 1 to -1 and back and forth. And so what happens when this spins is you create an EMF with magnitude and with a maximum magnitude of NBA omega that bounces up and down as a sine wave. And this is how AC energy is made. This is what AC energy is. That any AC engine, first AC engine, AC generator, that any AC generator is just a loop of wire spinning in a magnetic field. You spin it, you create an AC power supply just like that. Okay? Now, if you want DC, you're going to treat DC the same general way we did for the modal. You can use that same split ring or the split rim communicator or slip disk so that as it spins, what side it's attached to flips every 90. You won't get a constant, you can't possibly get a constant DC electricity out of this, but it would make only the half a sine wave, well, like a sine wave that's always positive. So you at least don't have to worry about changing directions. It's not a very good DC power supply, but can be used as one. Now, this idea though, and this is, we're gonna get a little complicated for a second, so I apologize. That, okay, let's think about this making a generator, right? I'm saying if you go and spin a loop of wire in a magnetic field, you create a current. But earlier we said, if you have a loop of wire spinning in a magnetic field, if you have a loop of wire with a current in a magnetic field, it'll cause it to spin, right? That's the whole idea of the dichotomy between this motor and generator. This actually has some weird effects. Something known as the back EMF that happens when you look at generators or motors. And let's actually look at with the modal. That if I try to do a modal, and I have my modal set up below, which I have a split ring communicator, so it's always pushing in the same direction. And I make that modal. When I make that modal, I put in current. By putting in the current, I give it an EMF, I give it a voltage. By giving it that voltage, it causes that ring to spin. But the process of that ring spinning creates an induced EMF. What happens when you have any modal that's made like this? It'll act like there's a second battery inside of it. And the power needed to make the motor spin is going to be reduced by what is called the back EMF, which is the induced EMF. Because I'm just going to let this play for a second more, because that's what's going on. That since the motor and the generator is the same thing, that the process of using this as a motor makes a generator, which makes a current or EMF opposing what you put in. Yeah. It's weird. Now, keep in mind, it only produces EMF when it's spinning. So if you turn a motor on, it'll have no back EMF. And as the motor spins up, the back EMF will increase. And then as the back EMF increases, if you want to have a constant power, you're going to have to change the power you put in. But if you're changing the power you put in, that's going to be changing the back EMF. And it's complicated. But this is a real thing you got to deal with when working with a AC or a DC modal. That the process of creating a DC or AC modal, you will, while it's running, the process of the AC or DC modal running will create a induced EMF that opposes the power going into the modal. Any questions on that? It's kind of a hard thing to explain, but I think I made it make some sense.
I think I got it.
Good enough for me. Okay. Now this idea that the process of running a modal makes it act like a generator, which lessens the power of the modal, which means the process of making a modal makes the modal work worse. This ties into an idea that that's called self-inductance. Let's say I have this simple circuit. I got a resistor, I got a battery, and a switch. When I do this, the second I close that switch, the potential from the battery is going to move some electrons. Electrons are going to move around it. We're going to have a current. And it's going to go from no current to there is a current right when I flip that switch. Now, theoretically, the voltage on that resistor should be the same as the EMF of the battery. And using V equals IL, we're going to have a EMF, we're going to have a voltage gain or an EMF of that epsilon, and the resistor is going to lose that same voltage. But let's say we make this loop just like that. If I make that loop just like that, I'm going to suddenly have a loop of wire. And a loop of wire has a magnetic field. So I'm going to go, when I close that switch, to having no magnetic field to, if I right-hand rule this, magnetic field into the page. But if we go from, I'm getting ahead of myself. So what I'm saying is when I close that switch, I'm suddenly going to create a magnetic field, which, okay, that's fine, whatever. But this is a loop of wire. That's what the circuit is. Any circuit is going to end up making a loop entirely because you have to have a closed loop for a circuit to work. And so if I suddenly go and turn on this circuit, I suddenly create a magnetic field. And if I suddenly create a magnetic field, I have to induce a magnetic field to oppose it. And so that means the process of closing the switch will induce an EMF. Now, if this thing's just running, let's say this is some magical thing that was started before the creation of time and has always been running, that is not going to induce anything. Because if there's just a constant current going, there's a constant magnetic field, we're not going to do anything unless the magnetic field is changing. This is only going to happen as the switch closes. Because as the switch closes, we'll go from zero magnetic field to magnetic field, which means we're going to induce a magnetic field to oppose it. But what that induced magnetic field means is an induced EMF. And so the process of that switch closing, we're suddenly going to act as if there is a second battery in the opposite direction of the first one. And so what would happen is that right when it closes, there's suddenly going to be, there's going to be the voltage of the battery and then another voltage induced EMF in the opposite direction. But that's only there when things are changing. And so what this does, so keep in mind, okay, sorry, before I get into what it does, because it's only if it's changing, that's what I just said. That means if the current stabilizes, the magnetic field doesn't change anymore, that means you no longer induce an EMF. Now this is called self-inductance. And it literally is what happens. If you take a circuit and you have just that simple circuit I have, and we go from open to close, the voltage does not instantly cover the battery. It does not say that voltage on the battery is voltage on the resistor is voltage of the battery. It's not instant. What the self-inductance does, which is inductance just by your own existence, it's why self-inductance, is it slows it down. What happens when you close this circuit is the electrons start moving. The electrons starting to move creates a magnetic field. That magnetic field is going to oppose the electrons moving. Sorry, I skipped a few steps there. The electrons moving is going to create a magnetic field. The creation of the magnetic field is going to induce an EMF. The induced EMF is going to oppose the electrons moving. But what will happen is over time, it'll balance. And over time, the magnetic field will stop changing. And since over time, the magnetic field stops changing, it stops inducing an EMF. And so what happens with a simple circuit when you close it is it doesn't instantly move all the voltage. That the voltage on the resistor starts at 0 and works its way up to the voltage of the battery. But it will still always eventually hit the voltage of the battery. Okay? Now, let's get a little further on this then. I'm just going to keep making it weird. Let's say instead I had a solenoid wrapped around a metal ball, right? So just a loop of wire wrapped around a metal ball. That's all I got. Just like my I don't have the video open. Just like the electromagnet video I had before. Now, we know the magnetic field in a solenoid is mu naught Ni. We covered that last chapter. Yep. Well, N is number of turns per length. And let's say that is what we put the current through. That we're going to take this solenoid, put some current through it. Well, let's say instead the current changes with time. And current changing with time, we could just do it with messing around with DC, but let's just hook it up to an AC power supply. We're going to talk about AC a lot more next chapter, but we know this idea that AC power supply, the current will change as a function of time. If I do this, if I hook that into a circuit, what I'm going to have is that as the current changes, we're going to induce an EMF. Because if I make this solenoid part of my circuit, what's going to happen is going to have a magnetic field. If I change the current, I change the magnetic field. If I change the magnetic field, I'm going to induce an EMF. Induced EMF means I'm going to affect the current. And what it's going to do is it's going to act like there's a little battery, a little induced EMF inside this solenoid. That if I is increasing, it's going to oppose it. If I is decreasing, it's going to push with it. And so if I starts to go down, it's going to try to push I up higher. And if I starts to go up, it's going to try to pull I back and keep it down low. It's going to try to restrict the changes. Now keep in mind, we can talk about the magnetic flux through our solenoid. Flux is BA cosine theta. Now in this case, I'm assuming it's wrapped around like this, so we can say it's at 0 degrees. And the magnetic field I said was mu naught Ni, so the flux should be mu naught Nia. Now, since we have an equation for induced EMF, I'll just plug my flux into that equation. And the only thing changing is I, so I'm going to move everything else out of my delta. And I get that the induced EMF is negative the number of turns times mu naught times the number of turns per length. So the number of turns shows up twice here, times the area. Delta I, delta T. And people found this is sometimes useful. Having a piece in a circuit that restricts change. Having a piece in a circuit that suddenly if the current goes up, it says, screw this noise, I'm keeping the current where it is and pushes it right back. Or having something that the current goes down, it's like, we're losing power, we need more power, and it makes more current. That's a useful thing to have in a circuit. And so people started purposely putting solenoids in our circuits, which will refer to the solenoids how well they can keep the current from changing as their inductance. Now the inductance, which is symbol L, is just going to be the property of that solenoid. It'll be the number of turns times mu naught times the number of turns per length times the area. And if we define that whole big thing as the inductance, once again using the symbol L, we can say for any circuit or anything that has this ability, any solenoid in a circuit, we can just define that term to talk about how the current would change as a function of time. Now, for the record, inductance, once again, use symbol L. It is measured in the units of henries. It's the guy's last name, is Henry. Okay. So that's it in general. If you have an inductor, if you have inductance in a circuit, if you have an electromagnet, you try to change the current, it's going to try to keep it from happening. If the current goes down, it's going to make it's going to do inductance to make it go up. You driving it up, it's going to try to make it go down. How hard it tries, that's inductance. Now, this was the equations if it was a solenoid, right? That I said that N mu naught Na, that was for a solenoid. Normally, when you put inductance in a circuit, you're working with solenoids. But if you just use this, if you multiply the top and the bottom of that by I, multiply by I over I, don't forget that B was mu naught Ni for a solenoid, that I was talking about a solenoid with magnetic field mu naught Ni, means I can say that this would be the same, that the inductance is given as NBA over I. Keeping track of what my flux is, and the inductance of anything else, if it's not a solenoid. But the inductance of any other thing will be N, the flux over the current. This first equation, let's just clear it out. This equation is the inductance of a solenoid. This is the inductance for anything else. Any questions?
No, no questions.
Okay. Now, I lost my mouse again. Sometimes you want inductance in a circuit. And when you do that, you add an inductor. This is an inductor. And actually, you know what? I'm going to switch to this because that way I can easier hold it into place. This inductor is literally, if you look in there, you can see there's some light work. In here, there's these like, you can kind of see there's some shiny bits. It's literally just wrappings of copper. This way I can see the light metal. There we go. It's literally just wrappings of copper. And it's kind of thick, but it's like literally just, come on, focus. There we go. It's literally just like lots and lots and lots and lots of layers of copper wire that you can kind of just see inside there. That's all an inductor is it's just a big electromagnet in the middle of a circuit. And by putting a big electromagnet or a solenoid in the middle of a circuit, you can control the inductance. And if you can control the inductance, you can control how the circuit works. Now, inductor is normally symbolized with a squiggly line. Be careful with your inductors versus your resistors. Resistors are jagged, inductors are loopy. Inductors use the symbol L, just like resistors use the symbol R for resistance, which is also R. That's what they are. I did have at school a demonstration to show how inductors work in series and stuff, but it was really old, and I decided to try it to make the video, and it literally started smoking, then sparked in 2 spots, and then flipped the GFI. So I just threw it out and didn't touch it again. So no demo here. So let's talk about what happens when you put an inductor in a series. Oh, sorry, inductor in a circuit. I misspoke. Inductor in a circuit. And we talk about all C circuits, a resistor and a capacitor in a circuit. But let's talk about how we put a resistor and an inductor in a circuit together. Now, if I don't have an inductor, if I just have resistor, right? I know voltage drop. Voltage drop over resistor is negative IR. I do the Kirchhoff loop. I can go, battery is how much voltage I gain, resistor is how much it leaves, so 0 equals EMF minus IR in this case. Now, I've already said that if I close this switch, there's going to be self-inductance. That self-inductance is going to slow how quickly the resistor gets that voltage. But honestly, self-inductance isn't very fast. It doesn't last very long. It's going to slow it down, but not that much. It's going to get the current pretty fast still. And keep in mind, we view current as opposition of current. Sorry, we view resistance as opposition of current. And so what would happen with time is we'd go from potential of 0 on the battery to, after a little bit of time, a potential of the same as the battery on the resistor. So 0 on the resistor to having a potential on the resistor. And it's not going to be instant because of the self-inductance, but it'll go pretty fast. Well, if we instead had an inductor, which I didn't do in this picture apparently, I thought I did. Where's my inductor? If we instead had an inductor, before the switch was closed, I was 0. But when the switch gets closed, suddenly there would be a voltage increase on the inductor. And what would happen is that an EMF, an induced EMF, would be created in the inductor equal to the magnitude, but opposite direction. And so if you just put an inductor in the circuit and no resistance, it'll just make it not work. You flip the switch and it would act like the switch didn't close. The reason why is when you flip the switch, it would suddenly try to induce an EMF. Sorry, it would have an EMF, like because it's hooked up to the battery, that's going to be an EMF there. And the process of the EMF would put a current through our inductor, and the inductor would say, fuck that noise, and induce an EMF opposing it. And we'll keep the current at 0. See, resistance holds how much current you have. But inductance changes how quickly the current changes. And so you put the more resistors you put, that's just going to relate how much current we have for a given voltage. But inductors change the rate at which it happens, how fast they spin. If you just have inductance and nothing else, it'll make it so that it never can create the voltage it wants to have. But when you start putting everything together, a resistor and an inductor, it's kind of interesting what can happen. If I start with this, just open and everything, and close my switch, right when I close the switch, current starts flowing. Right when current starts flowing, an EMF will be induced in the inductor. And that EMF induced in the inductor will try to resist the battery. And it won't kill it all. If you have a resistor, it's actually going to keep it from killing it all, but it will slow it down, causing the current to build up slowly. And so instead of just going no voltage or no current, we got current, and even with the self-inductance, it's not instant, but it's fast. We can control exactly how long it takes, exactly how long until the current is at its max value. I mean, once it hits the max value, the conductor stops doing anything, but it will gradually put it in it. And this can be really useful in complex circuitry, because sometimes if you don't want to go, we got nothing, to holy shit, everything's going quickly, that could be jarring on a system that suddenly have a lot of current. There's heat loss involved and other things. If you go from no voltage on this resistor to a lot of voltage on this resistor fast, will mess things up. But this just lets you gradually work your way up. Go from nothing to a little bit, to a little bit more, to a little bit more, to a little bit more, to the max, and then just stays there. And that's what an RL circuit is a way to delay current rising to the max. Now we can work out the equations for an RL circuit. We're just going to use a Kirchhoff loop and say for this circuit, my loop is plus the battery, minus the resistor, minus the inductor. But I already said the EMF on the inductor is negative L change in I over change in T. Really though, that change in I over change in T should really be a derivative. Oh, those lines were not off correctly. That really should have been there. And I can do some calculus. We're not going to get into the calculus, but I can do some calculus. And if I do, I find the current as a function of time. That in all our circuit, the current as a function of time is the EMF over the resistance times 1 minus e to the negative t over tau, where tau is the time constant. Tau is L over R. Now this looks a lot like our C circuits, which had a very similar looking equation. And even had a tau in it, the tau was RC there. But it is a little different and it works a little differently. You could also find the voltage over the resistor. The voltage over the resistor will go as follows. Okay. Now, that's saying that once we close this, that's how the current and voltage changes over the resistor. It has that max value and then it just stays. Now, if you then go and open this, well, once it's going fully, there's a magnetic field in our inductor. And if you go and break the circuit, you're suddenly going to try to remove the magnetic field from the inductor. If you remove the magnetic field from the inductor, it's going to induce an EMF. And so if this has been running for a while and you open the switch, the current and voltage will also change as a function of time. That you would think you open the switch, it just dies instantly, but it doesn't. You open the switch and it powers down. If you ever play with some like old electronics that have a light, often when you turn it off, the light doesn't turn off, it dims to nothing. This is why it's from an inductor. That it's not just making it just cut off entirely, but slowly bringing it down. Okay? So in general, all our circuits, when the battery turns on, that's the voltage and current as a function of time. When the battery turns off, that's the voltage and current as a function of time. I am going to end a bit early today. I don't have much left. A little bit left. You good so far?
Yep. All good.
Okay, let's do a practice problem. We calculate the resistance in an all-hour circuit where L is 2.5 henries and the current increases to 90% of its maximum value in 3 seconds. Okay, so I'm saying the current is 90% of its max value. It increases 90% of max value, so I'm charging it. Because I'm talking about increases too, that has to be going up. So I'm going to use the charging equation. And I want current, so I use the current charging equation. Now the maximum value, that's just the EMF over O. Really, this first equation can be written just like that too. And what we're saying is that 3 seconds, it's 90%. What that means, that is at 90%, it means the current divided by the max current is 0.9. And I can just say that instead of I equals I max 1 minus E negative T over tau, that's just going to be 0.9 equals 1 minus E negative T over tau. I'll add my exponent thing to both sides. I'll subtract 0.9 to both sides. And 1 minus 0.9 is 0.1. The inverse of E is a natural log, which means this. You can look up the natural log of 0.1. I did it. The natural log of 0.1 is negative 2.3. So negative T over tau equals negative 2.3. Or T over tau equals 2.3. I multiplied both sides by tau. But keep in mind, tau is L over O. And plugging that in, I can multiply both sides by O, divide both sides by T. Plug in, get a value. Now, I'm going to state something right now. These equations that I just gave, all of these, I didn't say this. This was mostly for DC circuits. All these here. If you're dealing with AC circuits, it's a little more complicated. We're going to cover that next chapter, though. I forgot to say that. And by it's a little more complicated, I mean it's a lot more complicated. You notice that I had an EMF of a battery in here, so it had to be DC. I meant to say that before. Also, one last final thing is that if I take my inductor and have current through it, that if there's current through this, I'm going to be creating a magnetic field. If I'm creating a magnetic field, there's some energy involved with that. Anytime you have an inductor, if you have current through the inductor, the EMF induced by the inductor is going to prevent things from happening right away. And since the battery is using energy to push things forward, and if the inductor is keeping that from happening, What that means is that an inductor must be affecting energy. And anytime you have an inductor with a current in it, it'll store a certain amount of energy stored in the magnetic field. It's a type of potential energy. And in this chapter, just like before, we're gonna we talked about the internal energy of a capacitor. Where we said the internal energy of a capacitor was U sub C. We can talk about the internal energy of an inductor. And the internal energy of an inductor is 1/2 Li squared. Okay. Now, that is actually the end of this chapter. As I said, I'm ending a bit early today, like 15 minutes early. So cool. I will add that today, assuming you're watching this the day I'm filming it, aka the 7th, there is no homework due because this chapter, we just are finishing it now. The homework for this chapter will be due next Wednesday. You do still have a lab due tomorrow because the lab is about charged particles in a magnetic field. So that's stuff from last chapter. And I'll release a lab tomorrow for this chapter where we will look at, I want to say it's an OL circuit lab is the one that's released tomorrow. I'm blanking off the top of my head. Yeah, it is. It's an OL circuit lab. We'll do practice problems Friday. And then next week, we'll start actually dealing with AC. And next chapter will be our last one on electricity and magnetism. That will do electricity and magnetism next chapter with AC circuits, and then we'll move on to other things. Other than that, if there's any questions, I'm going to stop there. So have a good day.